First of all, I totally forgot to have you turn in a potential test question yesterday, which is my bad. I was going to have a quiz today, but I can't because I don't have any quiz questions to give you. So remember, before you leave today, to turn a potential test question. Obviously, Leslie didn't have any, but now Leslie got, this would be more than enough to last you the entire semester. There's stuff for you. And anytime you need more, just grab more. But make sure that during the lecture, you just, no, go ahead and keep all this. Keep it so next class period you have one, next one you have one. So as we go through the lecture, when you think, here's something that'd be a good question to ask on a quiz or a test, write it down and remember to turn it at the end of class. Also, those box numbers. On that form, put your box number, because if you sign to say that I can put stuff in a box, there are boxes on the other side of this wall where we will return things like your potential test questions. So make sure you, if you don't want them out there in the box for other people to see, then check the box that you don't authorize, and then you'll have to get them directly from me. But then make sure you have that box number so you can put it on assignment so we know which box to put them in.
Oh, so we choose our number?
No, it's, oh, you don't have one. Here we go. Do you have a syllabus?
No, but it's okay.
So here, have yourself a syllabus and a box number thing. Okay, and so please turn those permissions for us to put things back in the box number as well when at the end of class. 3 people have already turned them in. Mariah did really well because I totally forgot in last class where she turned hers in anyway. Right, that was better than me. Okay, we are in chapter 1. We should finish chapter 1 today. So we're going to be talking about forces. We already introduced forces. Forces are anything that pushes or pulls. And we'll talk specifically about these 3 forces: the normal force, the force of friction, the force of gravity, Newton's laws. We'll talk about Newton's 3 laws, and that'll probably get us to the end of the class period. So we had this slide last class period, but it's a good introduction to the force of gravity. The force of gravity is an attractive force. It's a force that pulls things toward each other. And for our beginning study of gravity, we're only going to talk about the force of gravity because of the Earth. Why the Earth? Because the Earth is a really massive object. There's a lot of matter in the Earth. And since it has all of this mass, the force of gravity between the Earth and other objects is pretty large. So you sitting there in your chair, you can feel yourself being pushed down into the chair because of that force of gravity. And that force of gravity, through careful consideration, we have found to be proportional to the mass. One of the 2 definitions of mass was the gravitational mass. So the force of gravity is equal to the mass of an object multiplied by a constant that we call g. So that's, the name of it is the acceleration of gravity. Now the word acceleration will probably come up as well today. Notice remember I specifically didn't talk about acceleration in lab yesterday. Acceleration is the rate at which speed changes. So acceleration is the rate of change of speed. I mentioned rate in lab yesterday, but rate means basically how much per something else. And without qualifying, it's going to be how much per time. So in equation form, acceleration is the change in, remember the delta, change in, and then what was our symbol for speed? It's actually a V. I write it as a script V over delta t. as a physicist, we learn to write certain letters certain ways, still maybe sloppy, but we try to write our V's as a script V so it doesn't look like the Greek letter nu. That's a nu. And so we write them differently so we can distinguish them. So delta V over delta T, change in speed over change in time. Now, truthfully, acceleration is a vector, and it really needs to be written as a vector equation. So instead of A equals delta V over delta T, how should I change that to make it a vector equation? Vectors have direction, and we indicate that by the arrows on the top. So the acceleration vector is equal to change in velocity vector over change in time. Now, something interesting about acceleration, we usually think of when you're in your car and you press on the gas pedal, sometimes we call it the accelerator. And you press on the gas pedal and your speed should increase. And that's an acceleration. It's a change in speed that occurs over time. But there's another pedal that you can press that will also change your speed over time. What's that? The brake pedal. So the brake pedal is also an accelerator. It just accelerates you in the opposite direction you're traveling. Sometimes people call that deceleration. Deceleration just means acceleration opposite to the direction you're traveling. I tend to try not to use the term deceleration just to not have too much jargon. There's a third thing in your car that you can use to accelerate your car. Another thing you use for driving. And I'm not, some people say, well, the shifter. No, it's not the shifter. What else can accelerate the car besides the gas pedal and the brake pedal? It's not obvious. Leslie knows. Go ahead and tell him, Leslie.
I don't know much about cars. I'm trying to think. You said this in physics, but I don't remember anything.
Yeah, okay. The steering wheel.
Oh yeah, there you go.
Because velocity is a vector, even if you stay going the same speed, if you change directions, you've changed velocity, and hence that's an acceleration. And so the steering wheel is also an accelerator. It also will accelerate the automobile. So you have three things that will cause an acceleration. Now, all of that was tangential to what I really wanted to get to, units. Change in velocity over change in time. What are the units for velocity? Velocity was blank over blank. Fill in the blanks. What was velocity?
That was change of distance over time.
Yeah. Distance, or the vector form or the scalar form, right? Speed, distance over time. Vector, we say displacement over time, but it's the same idea. So it's distance over time. The unit of distance is the meter. Unit of time is the second. So the velocity units or speed units are meters per second. And of course, time has units of seconds. So that means acceleration must have units of meters per second divided by seconds. And some people write this in the most absurd fashion possible. Meters per second per second. Technically right, but confusing. You could also write it, and this is probably confusing to you, but to me it's not, because I've been dealing with it since before you were born. Meters per second squared. All three of those are technically right. The first one and the third one to me makes sense. The first one, meters per second, that makes sense. It's a change in meters per second every second. The last one to me makes sense because I'm used to it. For most people looking at it, doesn't make sense, because what's a second squared? There is no way to put a physical meaning to a second squared. But that per second squared means meters per second per second. If you think about it that way, then it starts to make sense. The key is the units for acceleration are these, and I'm almost exclusively going to use that form. So we call this the acceleration of gravity because it's an acceleration term. It has units of meters per second squared. The value of g averaged over the surface of the Earth. Actually, it's not averaged, I don't think. I think it's just the most common. 9.80 meters per second squared. You'll find some textbooks that say 9.81 meters per second squared. You basically go with what your textbook says. You know, what's the difference? It's like 1% roughly. It does vary a little. It's going to be a larger value if you're at a lower elevation, a lower value if you're at a higher elevation. So the force of gravity, which we call your weight, is going to be slightly lower if you go up to Pikes Peak. So if you go up to Pikes Peak, you lose weight. A very small amount, mind you, but you lose weight. What happens to your mass if you go to Pikes Peak? Stays the same, right. The weight changed because the G changed a little. But the weight stays the same because the mass stays the same because that's a measure of how much you have, but the weight changes because that's the force caused by gravity. Now notice our textbook has 1 kilogram and 10 N. Well, if I just take this equation and I say my mass is 1 kilogram, I should have 1 kilogram times 9.80 meters per second squared is 9.80 kilograms times meters per second squared. So there are two things. Number one is, why do they have a capital N instead of kilogram meter per second squared? The answer is, we physicists, instead of saying lazy, let's say we're economical. We don't want to write kilogram meter per second squared all the time. And we talk about forces a lot. And so we make a new unit name that's the Newton, named after Sir Isaac Newton. And that Newton stands for kilogram meter per second squared. So the Newton is, we call it a derived unit. It's a unit that's made up of other units that are basic. Kilogram is basic, meter is basic, second is basic. Newton is a derived unit that's made up of kilograms, meters, and seconds. Now the second question is, why does the textbook have 10 written here when I have 9.8? The answer is disrespect for you. Not really. The author is taking the point that numbers are probably not your strong area. And so let's keep the numbers simple. And it's a lot easier for people to multiply by 10 than it is to multiply by 9.8. So if we just approximate that 9.8 is only a small amount away, 2 parts in 10. So what is 2 parts in 10? 2 parts in 10. No, 2 parts in 100 basically. So it's basically 2% error to say that it's 10. And it's a lot easier to do the calculation. So that's why it has the 10 there. Now in words, his words were correct. 1 kilogram of material weighs less than 10 newtons because it weighs 9.8 newtons. But what he wrote was the 10 newtons just to make the math simple. And we'll see that coming up multiple times where the textbook will just use 10 meters per second squared for the acceleration of gravity just to make it simpler for you. Now, we've already talked about density, the mass per volume. I'm just going to go right past that and get to net force. Net force, the word net means the total after you add everything together. So when we talk about the net force, we're talking about the total force. So we have the total force acting on something. So if you look in this diagram in the uppermost picture, we have 2 5-Newton forces acting on it. So the net force is 5 plus 5, 10 newtons. Does that make sense? Now on the second one, we again have 2 5-Newton forces acting on it. And the net force is 0. What's the difference between the two? It's the direction. When you're doing the net force, because these are vectors, you have to add them as vectors. And so the upper one really should have been 5 newtons to the right plus 5 newtons to the right is 10 newtons to the right. And then the center one, 5 newtons to the left plus 5 newtons to the right is 0 newtons. And of course, the bottom one, 5 newtons to the left plus 10 to the right, is going to be 5 to the right. So when you're finding the net force, you have to keep in mind the directions. The easy way to do adding of vectors is to just do it graphically. Did you guys learn to add with number lines when you were kids? That's exactly what graphical addition is. So I can take these and I can say I have my first 5 newtons. So I start at 0 and I go over 5. And then at the end of that, I add my second 5 newtons. And what do I have for my total? Going from here to here, I have 10 newtons. Or if they're in opposite directions, like the second picture, 5 newtons. From the end of that, I put my second, but it was going the opposite direction because of the arrow. And then we can see going from start to finish, well, I'm at the same place, so it adds up to 0. And for the final one, 10 newtons plus 5 newtons leaves, we call it the resultant, going from here to here, from where we started to where we ended, leaves 5 newtons for the net force. So in each one of these, the pink one was the first vector I was adding, the green one was the second vector I was adding, and the purple was the net force. So we need to be able to add these net forces for a very simple reason, because Newton's second law uses the net force, and we're going to have to use Newton's second law a lot. So we're getting now to Newton's laws of motion. Newton's laws of motion, I just love to tell the story of Newton. Newton, like many other people in life, was a slacker. And so in grade school, of course, in grade school, he goes to school and the teachers are doing just what I'm doing to you, boring him. And so instead of trying to learn from the teachers, since the teachers were already talking about stuff he understood, he did things like make little inventions to impress the ladies. And so after he finished his compulsory school, he wasn't doing very well because he didn't pay attention. And so people said, well, school's not this boy's future. And his mother had died, or his father died sometime around when he was born. And his mother remarried when he was 2. And his stepfather said, I married her, not the kid. Kid's got to go. And so he was raised by his grandmother. But people were looking out for him, and they found him a job as a shepherd. So now we have Isaac Newton, shepherd boy. The shepherd boy has but one responsibility, and that's to keep the sheep, keep them from wandering off or something from harming them. But Isaac Newton, once again, made his little inventions instead of watching the sheep. So he was a failure as a shepherd boy. And people said, well, this guy's really brilliant. I mean, look at all these little inventions. We got to find a way to harness that brilliance and get him back in school. So he found sponsorship, went to school where he still was kind of a lazy student, as I understand, until it got to his last year in college. And he's like, oh, crud. If I don't get my act together, I'm going to have to go back to a job. That wasn't any fun. So his last year, he actually put it all together, did a good job. He was hired on as a house scientist, which basically means he's now a scientist, junior scientist working in the college. And then the greatest thing that ever happened to Newton occurred. The Black Plague. Yay, hurrah! What did the Black Plague do? Killed everybody. I think it was 1/3 of the population died or something like that. And so it's a communicable disease. They weren't exactly sure how it was communicable, but they knew if we have all of our young, bright minds together in one place and one gets sick and dies, they all get sick and die. And we don't want to kill off a generation of our wisest youth or smartest youth. And so school was canceled for almost 2 years. And of course, for you and me, that also probably would have been one of the best things in our life, to have no school for 2 years when we're 21 years old. For him, it was a job now, couldn't work. So he went back to his grandmother's house, and if it was me, my sister's house in Huntington Beach, I used to spend every summer there until I got married, because why wouldn't you? It's where I would be. He was like, I can do nothing but physics. I don't have to worry about pesky students. I love my students. I don't have to worry about grading. I hate grading. I can just spend all my time on physics. And so during those, it was about 18 months, he came up with 3 laws of motion, what we're going to talk about right here. He came up with his universal law of gravitation, an explanation for how gravity really works, which lasted until Einstein. We still teach you that because it's still fundamentally correct. And unfortunately, there was no math in existence to solve the problems he was working on. So he invented calculus so he could solve his problem. So it was a really good period of time for him. Things you may or may not know about Sir Isaac Newton: he was a very religious man. He wrote about as much about theology as he did about science. And I am told, I've never read his, but he wrote a set of Bible commentaries that are actually very similar to Ellen White's Bible commentaries and interpretation. He also had a short, brief stint as a politician. He, from what I've read, is only on record as speaking once in Parliament. And of course, when he stands up to speak, everybody's like, ha ha ha, the great man is finally going to say something. And what he said was, it's a bit drafty in here, could we close the window? So probably wasn't a great politician, but a great man. His first law is the law of inertia. He took the idea of inertia, as Galileo had introduced, and put it into a law. That is, he took the understanding and put it into a formalism that has become widely accepted. And so that first law says an object in motion stays in motion unless there is a non-zero net force that acts on it. So basically what that says is you'll have constant motion, that means constant velocity, same direction and same speed, unless there's a force acting on you. So if I take this pin and I let go, it doesn't just hover in the air, it changes its velocity, it speeds up. So according to this, it has to have a force acting on it that's making it speed up. If it's on the table, there's a force of gravity acting on it, but it's not speeding up. Because it's not speeding up, we can say, because of this first law, that the net force, the sum of all the forces acting on that pin, are 0. So that's the first law. When you have no change in velocity, you have to have a net force of 0. The example I used was stationary, but it doesn't have to be stationary. So this is an example. This young lady is pushing the table at constant velocity. If it's at constant velocity, what's the acceleration? How do velocity and acceleration relate?
So if the velocity is constant, then the acceleration would be 0 because there's not a change in speed. Like if you're just going constant, then there's no acceleration because there's not like as if you're pushing and then I don't know, you push harder and it goes faster, then you're accelerating.
That's right. Acceleration results from a change, or acceleration is a change in velocity over change in time. So if the velocity is constant, the acceleration is 0. And we call this situation where it's a constant velocity equilibrium. even if it's moving at constant speed. So you're driving the car 60 miles an hour on a straight road, that's constant velocity, and we call that equilibrium. Equilibrium has two words. The first one is fundamentally equal. Equal. The second one, librium, is a little more confusing to a lot of people. Librium means here force. So equilibrium means equal forces, or putting it in layman's terms, the net force is zero. And that whole librum thing, meaning force, what's the abbreviation for pounds? LB. What does that LB stand for? It stands for this. So we actually measure our forces in the imperial system in libras. So that's what the LB is, which is extra confusing when you measure the air pressure in your tire. It's PSI, which is pound per square inch. So then it's using pound instead of LB. Nice. Okay, so equilibrium occurs when you have the net force is zero. First, oh my goodness. I swear I have this running, but yeah, I didn't hit start. That's why. Now, I think that everything's going to work right today. First clicker question, remember it's either channel 33 or if you're using your smartphone, web.
What channel is it?
Either 33 if you're using the regular channel on a clicker, or web SCNC, web SCNC if you're using a smartphone. Waiting for two people who are both fastidiously working on their devices, so I assume that it's a good wait. Okay, we should have a lot more clicker questions today. So I'm going to move on. As long as you answer 2/3, you get credit. So keep working on it to make sure that you're going to be able to answer the next one for the two of you who don't have an answer in right now. Excellent. It still didn't show me. Did it show you? I'm not sure why it's doing that, but it's only the first time that it doesn't show me. Okay. Everybody answer again real quick. Yeah. Okay, somebody just came in who, that must have been you then. So now it's just Ashton that doesn't have it in. Please work this time. Yay, that time it worked.
It got like all the way and it says like put in the session and now it's asking for a user ID again. It just keeps going in a loop.
Okay, we had here the answers. Nobody said the top or bottom ones. 2 people said move steadily in a straight line path, and 5 said both. So Rachel, I randomly chose your card. So what was your answer and your reasoning?
I answered B and move steadily in a straight line path. I wasn't sure if the at-rest one was too, but based on what we were just talking about with the table, that's.
Okay, what we were just talking about with the table was moving steadily in a straight line. So she answered that one. The correct answer is both. You weren't sure about the other. At rest, the velocity is 0. That's not the indicator. the rate at which it's changing, if it's constant at 0, it's not changing. And so if the velocity is not changing, you're in equilibrium. So it was both moving steadily in a straight line, that's constant velocity, and at rest is constant velocity. Question, Leslie.
These potential test questions,
Mm-hmm.
I still don't fully understand. Do I have to write one of those or something?
Oh, okay, no. You're writing something that I said from the lecture, not something from the textbook. If I find it in the textbook, you get 0. Right. So it needs to be something from the lecture. And the goal is to find something that's reasonably unique, something that is not too hard and not too easy. The whole Goldilocks thing. If it's too hard, no one would get it right on the test. If it's too easy, it wouldn't have any discrimination. Other questions? Things working any better yet, Ashton?
I'm gonna have to go back to it. It's not working again.
Okay.
I had it working yesterday too.
That's life. Okay, like this. I had this working yesterday. And it works after I come back to the questions. Maybe I just need to put a dummy question in to start, and then it'll work after that. Support forces. Support force is a term the textbook uses for the force that keeps object A from going through object B. So I'm standing on the floor. I'm not going through the floor. So there's a support force. The floor is putting a force on me, supporting me so I don't go through. I could do something similar. I can push on the wall. There's a force that the wall is pushing on my hand to keep it from going through the wall. That's also a support force. The term we use for these technically is the normal force. So you see I have there red the normal force. Normal does not mean ordinary. Normal is a trigonometric word, I suppose. Normal means a specific direction. D-I-R-E. So normal is the direction out of the surface. It's the direction the force has to be to keep something from penetrating the surface. So what direction does the force of the floor have to be to keep me from falling through the floor? It has to push up. So the normal force on me as I'm standing here is up. When I push on the wall, what direction does the wall have to put a force on me to keep my hand from going through the wall? It's normal by definition, and it's going to be now horizontal. So the normal force is the direction coming out of the object, and so the normal force is that force that's keeping something from going through the floor. Now, as we go through physics, we get really used to things like, I take this remote, I place it on the little wood. The remote has a force of gravity pushing down and a support force, a normal force, pushing back against that. It's in equilibrium, so we know the net force has to be 0. So just as in these pictures, like in the picture of the textbook, we have those forces and we know the net force is 0. So we have the force normal, the force of gravity, the net force, which we write like this often, that's the Greek letter capital sigma, and it means sum. So sigma F technically means sum of the forces, which is the net force. So I add up the forces. I have one up, one down. I'll just consider up positive. If the net force is 0, then force normal minus force of gravity equals 0. And since force of gravity is mg, then we get the force normal as mg. So people start to just think, oh, force normal is mg, it's the same as gravity. Not so fast. If you have the picture that's on the left there, you have the person pushing down on the spring. If we look at the table is going to have an upward force pushing against the spring. The spring has a downward force of the hand pushing down, plus a downward force of the weight of the spring. And so the normal force is going to equal the sum of the two downward forces so that the net force is 0. Hence the normal force caused by the table is bigger than the weight of the spring in the one that has the hand pushing down on it. Or similarly, if I just push down on this remote, the normal force is going to be bigger than the weight of the remote. So keep that in mind. Normal force does not always equal gravitational force. Often it will, but many times it won't. Okay, next question. Based on real life. Oh, really? Now it just doesn't start the polling. Okay, now it's polling. Did you get it, Ashton?
I'm
Trying again. I don't have time after class because I have back-to-back classes, but I would be happy to help you sometime outside of class. Or actually, Debbie Intersayer is the one who's totally in charge of these things. So when you stand on two bathroom scales with 1 foot on each scale and weight evenly distributed, each scale will read. Okay. So Sam and Mariah. Sam. All right, everybody's answer. Please work right. Boom, yes. 3301. Okay, this is a good place for you to talk to the people around you now that we have 3 tables. Talk to the other people at your table. I mean, I know Sam was by himself before, but now that you have some at your table, talk to the other people at your table about your answer and why you gave your answer, and see if we can come to something that at least gives the majority.
So then I'm wondering if that fits right here, if we can easily distribute. I didn't know, I like it, but I put, oh, it might be. That's right.
It doesn't feel, you're not holding all of them, you're sharing it with
Yeah.
someone else.
Well, because that's because you have 2 different doors on the bottom, so it's more, but it's the same options.
But it's not gonna feel like I'm holding all of the weight. Which
Yeah.
means like the scale. Like when it, you know?
I don't know.
I just chose it.
I don't think it'll ever be more.
Yeah.
It won't
I don't
be
think it
weird,
is.
no, I don't think it's gonna be
Maybe it's the same.
more. Okay,
Yeah.
I'm not holding all of them.
That's the good physics, let's test it.
I'm just thinking about like heavy as like all of them. Like I'm not something to like I'm like I weigh like 100 and I feel like I'm holding 100 pounds. If there's no
Okay, let's go ahead and answer this question again, and then I'll discuss it. I do love that you guys are taking it seriously and discussing it, not like, hey, it's cold outside. Okay, everybody answer again on the clickers.
Are we changing them?
Yeah, we're answering again to see if the discussion helped or hurt.
I can like hold up the
I'll change it. That was very thin. Oh, well. I'm going in.
I'm sure I did not read that right. I thought it was a P.
My marker is like right now.
Oh, okay, I can see what you wrote. All right, everybody has answered.
There we go.
So we have counting Ashton. Yeah. 0602. Okay, this is the way it's supposed to work. As you talked amongst yourselves, you move toward the more correct answer. Practical experience. My brother, my little brother, used to have a big weight problem. And so he was going to have a bariatric surgery, a duodenal switch is the name of the surgery he was having. And before you can do the surgery, you have to know how much you weigh. But when you weigh as much as he did, you can't get a scale to weigh yourself. And it's really embarrassing to go to the laundry and say, can you weigh me? And so he just went to Walmart and purchased 2 scales. And then he says, okay, so I put one foot on one and one foot on the other, and I read the 2, and then how do I determine my total weight? And it's really embarrassing because I had to stop and think, here I am, a physics professor. And yes, Ivy is right. If you look at the man, the green suited dude, what forces are acting on the green suited dude? What forces are acting on him? What's pushing or pulling on him? Okay, there's a normal force. He has a foot on each scale, so there's a normal force from each scale. And what else? And then there's gravity pushing him down. And now we were given here the weight is evenly distributed, so these are equal. And is he accelerating? Is he changing his velocity? No. So he's in equilibrium. So we have the sum of the forces is 0. So once again, I consider up as positive. And so I just add those 3 forces up. This diagram that has the force arrows we call a free body diagram. It's a diagram showing all the forces on the one object I'm interested in. And so then I just use that and say the up arrows are positive. So force normal 1 plus force normal 2. And then the one that's down is going to be negative minus force of gravity. And since these are equal to each other, 2 force normal 1. Wow, that was really nice. 2 force normal 1 minus force of gravity equals 0. If I want to solve that for force normal, I'm just going to add force gravity to both sides. And then I have 2 force normal 1 is equal to force of gravity. Divide by 2. Force normal 1 is force of gravity divided by 2. So if it's evenly distributed, half of the weight will be on one scale, half of the weight on the other scale. If it's not evenly distributed, you don't know, but you do know. So even if my brother didn't have his weight evenly distributed, if I add up the weights from both scales, it's still going to tell me how much you weigh. So we didn't have to sit there and make sure we get it exactly even. Just had to get both at the same time. Yeah.
So it's because of the 2 force normals, that you just add them up, that it's able to do that? Because, when you're trying to get someone's weight and then you're like there, and then the 2 force normals are pushing up on it with gravity on it, is that why you can add it?
Well, you can add it because of this equation right here. We haven't gotten to Newton's second law yet, but that's fundamentally Newton's second law. By the way, we're not going to come close to finishing today's lecture. Sad, but true. Because we got 6 minutes left and I'm like halfway through. But because you're in equilibrium, you know that the sum of the forces is 0. You have only 3 forces. If you can read 2, you can determine what the third one is just by that equation. A new force, friction. We've talked about the normal force or support force. We talked about the force of gravity. Now we have the force of friction. Force of friction is a force that acts between 2 surfaces. So, of course, the most common thing we think about is the force of friction between our car tires and the ground. At least that's what I think about the most. But we have other important things like the force of friction between my feet and the ground. It's really important. If there's no force of friction between my feet and the ground, when I start to step forward, my weight comes in front of my foot, and the back foot would just go sliding out if there was no friction. And in fact, you wouldn't be able to walk at all if there was no friction. Friction is what's keeping our feet from sliding with the ground. We have 2 kinds of friction. Static friction, that is the friction when the 2 surfaces are not sliding against each other. and kinetic friction, friction when they are sliding. If they're sliding, then the friction is always in the direction opposite motion. So if I have this remote sliding to your right, then the force of friction on the remote is the opposite direction, to your left. And if I reverse it, force of friction reverses. So the force of friction is going to be opposing the direction that it's sliding. If it's not sliding, if it's stationary, then the force of friction is going to be whatever direction is necessary to keep it from sliding. So the force of friction, force between two surfaces, what causes it? In physics, we really, really care about why things happen. So knowing there's a force of friction is good. Knowing why it occurs, that's really important to us. Why do you think force of friction occurs? Haven't thought about it? When you have the two surfaces, there are a couple things that are acting to make that force of friction. Number one is that the two surfaces on a microscopic level are not going to be smooth, even if they appear perfectly smooth to us. On a microscopic level, they're not going to be smooth. And so when you get two surfaces together, you will have them conform a little bit. That is, like my fingers, if I put my fingers like this, they can conform a little bit so they slip down. And to get them to move, I have to raise them up first before they can move on each other. That's what happens when you have two surfaces that are still against each other. They will conform a little bit to each other, and you'll have to do a little lifting to get them to where they can slide. So that's one thing. Another thing is that while we don't even perceive it, there are forces acting, sticky forces between my fingers and the desktop. Or you don't feel it at all, but they are there. And you have to overcome those to slide. And so those are the two aspects that make you have friction. If it's already sliding, you only have the second one. If it's not sliding, you have both. And so the force of friction is generally larger if it's not sliding than if it is. So if you're driving your car and all of a sudden something comes up in front of you and you hit the brakes, if you skid, you're going to have what we call the kinetic friction, the sliding friction, and it's not as much friction. If you don't have as much friction, it's going to be hard to stop. Whereas if you brake as hard as you can but don't have the wheels sliding, you'll have more friction. You'll stop quicker. That's why we have anti-lock brakes in our cars. The anti-lock brakes, you press super hard on the brake pedal, and it brakes the tire until it detects that the tire now has stopped rolling and you're skidding, and then it releases the brakes. So it starts to roll again. And you think, oh no, right? I wanted to stop. But it releases them and immediately brakes again. And so it keeps braking so you're at the maximum you can get when it's not sliding. And so the anti-lock brakes give you an average frictional force that's bigger than you would have if you were skidding. Also has the added advantage that you can actually steer. So the anti-lock brakes make it much safer and you stop quicker. We will end with this clicker question because that's the kind of time we have. When Nellie pushes a crate across the factory floor at constant speed, notice that term because that's important, or that phrase, the force of friction between the crate and the floor is, and you're comparing it to how hard Nellie's pushing on it. So is the friction less than Nellie's push? That's A. Is the force of friction equal to Nellie's push? B. Equal and opposite. So B says the force of friction is the same direction she's pushing. C says the opposite direction that she's pushing. And D says more than Nellie's push. So friction is bigger than her push. Okay. And it went past and it didn't show me the answers. Well, crud. Let's just go. I'm sorry, we're out of time. The correct answer is it's equal and opposite to Nelly's push. Because it has constant speed, it's an equilibrium, which means you add the forces up, they have to be zero. So Nelly's pushing one direction, the force friction has to be the opposite direction, the same amount. Okay, I'll see you on Monday, not on Monday, because there's no school on Monday, Martin Luther King Jr. holiday. On Wednesday, there is a homework assignment due Wednesday. It's on Moodle. If you go to Moodle, actually, I know class is over, so if you got to run to another class, which I actually do, I don't begrudge that. But I'm going to go to Moodle here, maybe. Here it is. I was like, I know I got to have a link to it. And just show you where the homework is and remind you of the important thing about how to do the homework. So you go into the class in Moodle, which everybody's in. Go into the class, Sesame. Said the magic word. And you go down here to homework 1, or you can look over here at upcoming events. Look, there's homework 1 right there. So I click on homework 1. Note the thing in red, red background, yellow foreground. It's important. Unless otherwise noted, you must always give an explanation for your answer. If a calculation is involved, you have to show your calculation. Right? You can look in the back of the book for half problems and it tells you the answer. You can go to one of those cheating sites like Chegg and it tells you the answer for everything. I want some kind of information showing that you understand what you did. So there are 2 here where I said you don't need to explain. For all the rest, you need to have an explanation with it to get your credit.